Hi everyone, welcome to my channel. My name is Fikret. In this end-to-end course, we're gonna dive into amazing world of real-time analytics in Databricks. I'm excited to take you there. Before we go deep into transformation discussions, it's worth to have a brief discussion about two large transformation categories. They're called stateless and stateful transformations. The stateless transformations are the ones which can be applied to each of your rows independently. So examples could be selections or mapping, where each row does not depend on the previous row. A stateful transformation, on the other hand, requires preserving your state in memory so that you could apply transformation incrementally. So, for example, with aggregates, you would store this aggregate of your data until the end of your stream. Another example of stateful transformation would be stream-to-stream joins. Because with joins, you require matching keys from different streams, you need to keep these keys in a buffer, in a memory for some time so that you could execute this matching. Let's take a look at a few examples of stateless transformations. So in command 40 and 41, I have example of pipeline that applies select type of transformation. So I am using select expert method here to change the data type and parse some of the complex data types. And I also apply filter, which is also considered stateless. Another example of stateless transformation is deduplication transformation. So in command 42, I perform deduplication on my data frame based on 3 keys. It's recommended that you include your event timestamp as part of your keys because of the nature of this column. So it's natural to expect that event time would be part of primary key in any event stream. Now let's talk about aggregations. Aggregation can be divided into multiple types. So global aggregations are the simplest one. They work on an entire table level and you don't need to specify any keys for that. Grouped aggregations, on the other hand, require certain keys from your data set. So you basically group your data based on certain keys and then you apply aggregations. The time-based aggregations are a variety of grouped aggregations, and here you need to include a time-based column as well. So it usually makes sense to include event-based columns as part of your group key sets. And to do that, you have to specify window function, where your first argument will be that event timestamp. A second argument will represent the length of the window. And the third argument will tell how frequently your window should be triggered. Based on comparative values of length and the frequency, you will get different types of windows, which you can see on the right hand of this slide, which I have borrowed from Spark official documentation. So the simple window type is called tumbling, where you have window length equaling its frequency. So for example, here you have 5 minutes long windows triggered every 5 minutes. So with this kind of windows, there is no overlap. With sliding window, on the other hand, you get window which is longer than its frequency. So in this example, I have 10 minutes long windows triggered every 5 minutes. Obviously, with this kind of window, you get overlap, meaning that some events will contribute to multiple windows. The session window is little different than these two window types. With session window, you specify gap duration, and the window will not start until it receives the first events. So as soon as the first event starts, so in this example, let's say at 12:04, a window starts and it will continue until we receive events. Once there are no events for the gap period, then windows close until the next set of events arrives. And as I mentioned earlier, with aggregates, you can use append, update, complete. So it will depend on your sync type as well as nature of your aggregations. let's take a look on how aggregations work. So in command 45 and 46, I am creating simple aggregates working on entire table level. So although I am using group by method, I did not specify any keys here. So if I run this command, I'll get row count for entire stream. So right now this number is static because my stream does not receive any data. However, if you run this command while generating the data, you will see this numbers growing. In command 47, I have grouped aggregations with some keys. So in this case, I am grouping IoT measurements based on office and the sensor columns and calculate the sum of measurement values. Here is how my output data will look like. In command 48, I have example of time-based aggregate. So this aggregate is similar to the previous one, except I have included window function here, and as a first argument to window function, I have specified my event time, and then I say my window's length is going to be 1 hour. Because I did not specify Windows frequency, Spark will assume that this is a tumbling window based aggregates. Once I calculate aggregates, my command writes the results into this table, silver table, which I can query. So this is how my data will look like. So using window function, create complex type of column like this, where you have start and end components, which of course you can extract and parse if needed. When building stateful transformations, it's very important to account for late arriving events. So late arriving events are the ones which arrive to your processing system well after they were generated. So that could happen due to different reasons. For example, if you have device which emits events, this device may go offline. So sometimes later when it comes online, it will connect to your system and send your data. Obviously, the timestamps will be little before your actual system time. So this is a great diagram that describes that concept. I borrowed this from Spark official documentation. So in this example, I have 5-minute long windows that's being triggered at 12, 12:05, 12:10. And let's say some of the events that have been generated before 12:05 did not arrive to my system until after 12:10. So by default, if you don't do anything, this event needs to be included in the later windows, which will make your aggregates incorrect. So to handle this properly, the best practice is to delay the closing of each window. So in other words, you would specify some grace period or delay period. Each of your window will not be closed until that period. This is called watermarks. So in this case, if I want to handle my late arriving event properly, I would account for watermark of 10 minutes, which will ensure that my 12:05 window is not being closed until 12:15. So let me demonstrate that in an aggregate example. In command 50, I have aggregation transformations, which is event-based group by transformation. What's different here is that I have specified with watermark method, which requires 2 arguments: the timestamp column name and the duration of that grace period. So in this case, I'm telling wait 10 seconds before you close each window. Let's talk about arbitrary state management, or in other words, custom state management. So state management can be automatic or standard state management, which Spark does for any aggregations or joins by default. So basically it preserves the internal states and it takes care of internal logic of your aggregations. However, with Spark, you also have flexibility of implementing your own custom state management functions. There are many use cases that requires custom approach, So for example, you could create windows based on counts of a given key rather than specifying some fixed window length. So in terms of actual implementation of arbitrary state management, up until recent times, you could only do that within Scala. So there are two functions for that, map groups with state and flat map groups with state. And recently, Databricks added support in Python for arbitrary state management. You can do it using apply in pandas with state function, which we'll be exploring shortly. I have provided few key state management methods here. So get method is useful to receive the previous state of your state. And then you can use update to refresh your state. And then you can use remove method to remove the state. You may want to remove your state whenever it expires. So what expiring means? Sometimes when you apply some stateful transformations, for example, some aggregations, your keys are not evenly distributed. So for example, you may have some keys coming rarely. To account for that, you have to implement timeouts. So the way timeout works is that whenever you are processing your next macro batch, you set certain timeout based on either processing time or event time. And if your stream does not receive the data for some particular key during this timeout, your state expires. And based on your state's expiration status, you can perform certain tasks. So don't worry if it's a little hard to understand. So I'll explain this on a few examples shortly. I have few examples of custom state management. Let me start with the simplest example. So here I have stream from Silver IoT measurements table. In command 55, I have simple state management user-defined function called custom ag. And then here at the bottom of this command, I have stream, where I group by on two columns and call apply pandas with state method, and I refer to that function. So let's take a look at the function definitions. The function requires three standard arguments. The first argument is a tuple of your keys. Second argument is an iterator of data frames. And third argument represents your states, the previous state. Results of this function should be data frame iterator type. Within this function, my first command extracts the components of the key. So in this case, I have two keys, office and the sensor. So accordingly, I assign it to different variables. And then I use state arguments exist property. And if the state exists, I receive the previous state using get method. And then I have a loop logic here. And for each data frame, I check if the value of temperature measurement is above 23 and count number of these cases and assign to another variable. Finally, I summarize these two variables together. So this will give me number of times the temperature in some particular office has went above 23 degrees. And at the bottom, I use state update method to refresh my state. And then I generate the data frame with the new values. Another thing to notice is that we have to specify output schema of the data as well as state schema. So because in this case, my state is single variable, this is how my state schema would look like. And this is my output schema. So let me run this. This is how my output would look like. So as you can see, this is a very simple example where my state is single value variable, and I'm not using timeout here. Now that we know how arbitrary state management works, let's take a look at little advanced case. So in command 56, I have similar user-defined function. However, instead of storing one value in state, I store multiple values. So I'm calculating a number of times my temperature measurement goes above certain value. But I also calculate delta. Delta meaning how many times I have got abnormal temperature within this micro batch. And if we take a look at line 16, I update multiple variables here. Accordingly, when I receive old state values, I extract multiple variables from that state. And because I am storing more values in state, my state schema has additional variables. One thing to notice here is that one of the parameters I supply to apply in pandas with state function is timeout settings, and in both cases I used no timeout value. Now let's take a look at more complex cases where I have added timeout handling logic as well. So in command 59, I have specified processing timeout as an argument for apply in pandas function, which means that now I can add timeout logic to my user-defined function. First of all, I added conditional to check if my state has expired. If it's not, then I set timeout with the duration of certain period. So in this case, it's 1000 milliseconds. So this part of the code will work whenever I receive the state for certain keys. So basically, each time I receive the key, I set the timeout duration for that particular key. Once I stop receiving data for that particular key and my timeout duration expires, this part of the code activates, where I just receive the old state and generates the data. So timeouts based on processing time may, in some cases, not be ideal, especially considering that processing time can lag. So for example, if your events come with some delay because of device connectivity issues or because of distance between your device and your processing server, then this logic may not work for you. So in that case, you can use event timeout option within apply in pandas function. And to use that, you have to set timeout a little differently. So you can see that I am using set timeout timestamp method here, which works similar way as set timeout duration method. Another thing to notice here is that I also added watermark here, and because we have to allocate for certain grace period. Now my data is evenly distributed in terms of keys, so it won't be easy to demonstrate internal logic of this based on my data. However, here is a sample from the table where I am writing arbitrary state management aggregation data.